All right, welcome to lesson 8, significant figures. So our intention today is I'm learning the concept and procedures for significant figures. So what are sig figs? That's a short way to say it. And how do we use them? We'll talk about the definition. We have a little story to help contextualize this because it's kind of a tricky concept. And if we take the time to tell a story, hopefully it helps us remember it because humans love stories. And we're going to practice adding and subtracting with it and multiplying, dividing with it. And we'll apply it to density, which we just learned about. So, significant figures. Significant figures are the digits in an imprecise, meaning we measured, we calculated, we don't know that this is true out to a million decimal places. There are numbers that have real information that we've found, but not all the numbers necessarily are legit. A simple version is that numbers sometimes have these placeholder or empty digits that help us understand what number we're looking at, but they don't actually add any information. Okay? Example, half a candy bar is 0.5. 0.5 all by itself looks really icky, so we add the 0, but that 0 doesn't have any information. It's not saying anything. It's just there to look nice. Okay, so let's tell a crazy story. You see the ball here in a bucket. So I show you a partly filled bucket of tennis balls, like half full. I ask you how many are in it, but you can't take the lid off to count it. I give you an exact copy of the bucket with nothing in it and put it on a scale, and we hit 0 so that the weight of the bucket is gone. It's just the weight of what's inside the bucket. You put a ball inside the bucket and you weigh it and you get 40.0 grams on the scale. The balls inside my bucket, when you put my bucket on the scale, they weigh 400 grams. Well, if you take 400 grams and divide it by 40, you get 10. And you say, oh, well, then there's 10 balls in the bucket. You're right. Congrats, you did it. I take that bucket away, pull out the balls, put marbles inside. You put a marble in your empty bucket and you get a weight of 15 grams. But just to be safe, because marbles are kind of small, you're going to put 9 more marbles in and you get 150 grams. The marbles in my bucket weigh 1,095.0 grams. And that's a little tricky. Let's pull out a calculator. So you take that 1,095, you divide it by 15, you get 73. And you tell me, well, there's got to be 73 marbles in there. Okay, so we've done this twice. Is there a point? Well, I take that bucket away and I pour sand in this time, not marbles. You get 1 grain of sand and you put it in the empty bucket and the scale still says 0.0. You put grains of sand in one at a time. It's painstaking. It sucks. It's taking you forever. And it says 0.0 the whole time. Finally, after 2,113 grains later, it says 0.1. You decide to test it, so you add 100 more grains, but it still says 0.1. You start removing grains, but the scale doesn't say 0.0 until it's reduced to 2,078 exactly. Do piles of sand that are less than 2,113 grains weigh nothing? No, doesn't make any sense, but the scale is not precise enough to measure individual grains of sand. It won't notice them until there's enough. Roughly about 2,100 grains of sand is 0.1 grams. That's the best that we can guess from now. So we try to do the math. My sand bucket weighs 2,578.4 grams. The math would be 2,578 grams, that's what it weighs, divided by 0.1 gram per 2,100. You put it into the calculator correctly, and it says 54,146,400. Is there exactly that many grains of sand in my bucket? Are you sure? Exactly that amount. What if you were betting your phone on it? That answer's cap. Roughly about 54 million. That's reasonable. Yeah, it's about 54 million. That's pretty close. Now imagine you're doing this again, but the bucket has water, and you're counting individual molecules of H2O, those little ball and stick models we've looked at before. We ain't finding the correct or precise answer to that one, Chief. Significant figures keep our answers from being capped, being lies, being wrong. Okay, so let's go back to our example. In this example we have here on our screen, right, that one, any digit not a 0, green, in our example, is significant, period T. So if there's a number that's not 0, that is part of the answer. Zeros between those non-zeros, which is yellow, those are also significant. Zeros before non-zeros, like you see in blue, not significant. Zeros after are significant in one of two situations. If it's between the non-zero and the decimal point, or if it's after the non-zeros and the decimal point. Okay? So here's an example of adding and subtracting. So for adding and subtracting, we do it normal, like you usually do. Then we round to the place value, that's the column, remember, of the least precise number. The number that is basically is the furthest to the left on my screen. An example is the 10th place, right? The 0.6 is less precise than 0.23. So if we add, my example's a little bit off here, or a little bit different. If we add 120 to 42.2, you first get 162.2, very straightforward, but we're going to round to the tens place because that's the largest significant value that we have to get 160. All right, next up, multiplication division with sig figs. So figure out how many sig figs are in each number. You can see here we're counting off. There's 1, 2, 3, 4, 5 in the top number, and 1, 2 in the second number. And this one. Then we multiply or divide normally. We get that big number, but now we're going to round to 2 digits. I know my lights are off. It's crazy. And that's basically it. So example here, 12.0 times 3.0 is 36. It does not equal 36.0 because 3.0 has 2 sig figs, and 36.0 would have 3. This can be very tricky if you're not keeping track of how many sig figs you're dealing with. Now let's look at density real quick. A liquid has a measured volume of 8.2 milliliters and a measured mass of 15.07 grams. D equals m divided by v. So D is equal to 15.07 divided by 8.2. Now, my calculator says that big old number. But wait, sig figs, because that's not accurate. That's not for sure. 15.27 has 4, 8.2 has 2, so we're rounding to 2 numbers. So 1.8 G divided by CM3 is the real answer. And that's all we got to do. We're going to do some practice on this in our practice sheet. Good luck, and I'll see you next time.